let SIK of C be an element of R n by n. Conjecture. And now you're going to see why I taught you the way. I mean, hopefully you've seen it the whole quarter, but it's just, it's the gift that keeps on giving. You ready? So, of course, we needed n to be a natural number with I and k element of that index and I not equal to k. Those are the conditions on the shear matrix, right? What did you notice over there when we took the inverse? What happened to the thing inside of it? You took the negative one, right? You ready for something crazy? How do I check that the inverse actually works? What's the one thing I have to do to check inverses? To confirm, we want to show, WTS, that SIK C inverse times SIK C equals what? The identity, right? Thus, consider, and this is where I want you all to be like, Anderson, I'm too good for you. And I'm going to be like, yeah, that's true, you are too good for me. What was the conjecture that we made about SIK C inverse? What's the conjecture that we're making? Negative C, SIK C. What is SIK negative C? What would that look like if I were to actually look at the darn thing? So that would be IN plus negative C times what? EI EK transpose, right? So that right there, this is the actual rank 1 update of the identity that is defined to be that shear matrix. What's the other one? What's this one? IN plus C EI EK transpose. And I hope I've caught, just this week, I caught a student last night at like 9 something, not checking his dimensions. And I like cried myself. Well, I wouldn't say I cried myself to sleep because I still had to drive home, but I did cry a little bit, right? With joy, because he felt pain, right? And that made him, like, he immediately checked his dimensions. So of course, underneath this, what should we be doing always? Writing the dimensions. Have you done that a lot for these problems? Anybody make a mistake where you messed up? That's where the real learning happens. Mistakes are where the real learning happens, right? Any suggestions? What did we know? You remember this when we had A outside of B plus C? Do you remember what we could say? Plus A times C. So I don't know, do you want to do, and then there was also, this was called left distributivity. There was also something called right distributivity, right? In real numbers, it doesn't matter because they're commutative, but in this algebra that we're working with, these are no longer commutative. Do you have a sense of which one you want to do first, left or right? You want to do left, so you want to distribute this. Yeah, I was kind of thinking right distributivity, bring this one in over there, right? Is that okay? All right, so let's do that. Let's IN times IN plus C EI EK transpose. And then the other one would be plus a minus C times EI EK transpose outside of IN plus C EI EK transpose. Okay, so that was called right distributivity because I literally brought this through that addition, right? Anybody see the next one? It looks a lot worse than it is. It's like me, right? What's the next one? Yeah, and maybe for now, I'm going to just really go overboard here, right? Plus, now what? And there are some mathematicians that make fun of me for writing all my stuff down. They're usually very privileged people that are further along in their career. than I was as a student? Or people that are less far along? Oh yeah, of course I need a C in there, right? Okay. What do you know about In times any matrix? That's just In. What do you know about, so this is a constant. What do you know about constants through matrix multiplication? They pull out in the front. So I can pull that constant out, right? What about this? What is EK transpose times IN? It's EK transpose. So that thing doesn't change, right? So now I've got minus C, EI, EK transpose times, or yeah. One way to think about that is identity doesn't change the vector that it multiplies by. The other way to think about that, if you want to do it from the other side, EK transpose pulls off the kth row of the identity, but the kth row of the identity is EK transpose, right? That's another way to think about that, right? Either way, it doesn't matter. What about over here? What do you notice? These are all multiplications. This is an n by 1, 1 by n, n by 1, 1 by n. This in between, what do you know I can do with that c? Pull it out. So now I've got minus c squared EI EK transpose. Those right now are associated together. These ones over here are also associated together. Each of those is an outer product. So now we'll go real slow. What do you know about IN times EI? EI, and there's two ways to think about that. Number one is the identity doesn't change a vector, right? The other way to think about that is EI picks off the ith column of the identity. What's the ith column of the identity? EI. And remember, I did do this, right? I did just reassociate. There was a reassociation that happened there. How many of you agree that matrix multiplication is non-trivial? Yep. This is one of my biggest critiques of every linear algebra teacher that I've ever had a class with, and the entire field who've written books. So minus C, EI. Anybody see something quite interesting there? The rank 1 updates cancel, right? Now the question that we have is, what the heck is happening here? And what I want to do is I want to reassociate, okay? I want to group those two things together. Can I do that in matrix multiplication? Can I group other things together? Okay, and now I need a beard and a pipe. So I can like stroke my beard and puff my pipe and look stodgy. EK transpose times EI. How big is EK transpose? 1 by n. How big is EI? N by 1. What do you know about k and I? What do you for sure know about those two integers? They are not equal. So now I have a vector that has all zeros over here except in the kth column, and I have a vector that has all zeros over here except in the ith row, and the kth column is not in the position that's the same as the ith row. What happens when I multiply those? And in fact, this is something called the Kronecker delta function. Can you guess what's going to happen if they're equal? It's called the Kronecker delta function because you're literally just picking off. If they match, then you get 1 because the 1s are in the same location. If they don't match, then you get 0. Well, in this case, what do you know for sure? What's that? They don't match. Why do you know that? The definition of a shear matrix implies that I was not supposed to be equal to k, which means this thing right here goes to 0. And now I have a scalar 0 times EI. That's the 0 vector. The 0 vector times EK, the 0 matrix. Now I have c squared times the 0 matrix. The 0 matrix. I subtract the 0 matrix off anything else. What do I get? Yep. So now I have, I'll go ahead and write all that stuff out because I said it out loud, not write it down, right? and that 0 is, of course, n by n. Since, and what do you know about these two things? What did we just show? Just so much cooler than when rappers do it, right? I can't let go of the prayer that someday I won't be completely a nerd, right?